Hello! Welcome back. In this video, you will learn the basics of working in Schematic Editor. Okay, let's open Schematic Editor. I'm assuming that you already have Typhoon HIL Control Center opened. If you don't, open it. Schematic Editor is the first icon on the left. The first thing you see when Schematic Editor is launched are the recent schematic files. You can quickly go to any of your current projects. Of course, you also have dedicated buttons in the interface that you can use to create a new model, load an existing model, save the current model, etc. You can also use the same commands in the file menu. So let's now create a model and see how Schematic Editor actually works. To create a model, you can click this button here, Create a New Schematic, or you can go to File, New, and then New Model. What you see here is the Schematic Wizard settings. As you can see, when you are creating a new model, you have to choose the HIL device for which you want to create the model. In this case, the HIL 402 is chosen. You also have to choose the configuration ID. Let's briefly discuss configuration IDs because they are really important. To get additional details on what each configuration ID can do, just click the device table. As a result, you will get a table with different configurations displayed. So for example, you can see that configuration 1 has 1 machine solver and 3 cores for power electronic switches, while configuration 2 has no machine solvers, but on the other hand, has 4 cores for power electronic switches. So configurations are a means by which you can make the best use of available HIL device resources, depending on what kind of schematic you are making, with machines or with no machines, with a few or with many switching blocks, etc. In short, what configuration you use will depend on your model, i.e., the components in your model. Here, you can also detect hardware settings and load the current firmware from your HIL device. Down here, you get to choose the simulation method. You have 4 methods at your disposal: exact, trapezoidal, Euler, and bilinear. Normally, you will use the exact method as it works fine for the majority of cases. Other methods should only be used if there are memory constraints. Below the simulation method, you can access the settings for the simulation time step. You can leave the setting as it is, auto, which means that the system will try to find the lowest time step possible, having in mind the constraints of the HIL device and the complexity of the model. So let's now click Next. Here you can review all the settings you've just made. If everything looks okay, as it does, just click Finish. Alright. This blank space that you see is the canvas for your schematic drawings. You create your model by simply dragging and dropping the required components onto the canvas and connecting them together. All the components are located in the Library Explorer on the left side of the screen. The Library Explorer is designed to be very easy to use. Let's say you want to find a resistor. You can find it by typing the keyword into the search input box, or by navigating to passive elements in the tree view where you can find the resistor. Then just drag and drop the component and place it into your schematic, i.e. your model. You can rotate the component, it goes without saying, and you can change the resistance. To adjust the properties of the component, say to adjust the resistance of this resistor, you double-click the component and enter the desired value into the relevant property box. Also, by double-clicking, you can rename the component, R-line. Of course, you can do this with all other components as well. So let's add one more resistor and let's connect them. For connecting components, you just click the connector. When you move the mouse, you will see that you are creating a connecting line. To connect another connector, just click the connector that you want to connect to, like so. Another really interesting feature is the model initialization script. What does that actually do? In the script, you can define some variables. Let's say that R equals 1 ohm, R equals 1. Then, instead of always typing in the particular value, you can use the variable here by defining that the resistance R line equals the R variable defined in the model initialization script. This gives you a lot of flexibility as you can define particular parameters and changing them in the easiest way possible. Moreover, because this is a Python script, you can leverage everything that Python can do, including very complex things. You can even load parameters from the file, or if you're very proficient in Python, you can even write a web client that fetches a web page and grabs relevant parameters. Or you can take the parameters from GitHub, GitLab, or some other DevOps platform. So the fact that you can use Python here opens up a whole new world of possibilities and gives you a lot of flexibility. What else can you do? Well, you can add more components. Let's add a voltage source, and this time you can do it by typing in the search string into the Find Component box. As you want to add a voltage source, let's type it in and search for it. So, you drag and drop, then rotate, and finally connect. Now that you've added a voltage source, you can also add some voltage measurements. Actually, this is a very good idea because voltage measurements allow you to see them in HIL SCADA when you are running your simulation. Another feature available by double-clicking is that you can also turn on signal processing by setting the signal output to true. Now you have this terminal here, which you can use for signal processing purposes. So let's open signal processing here in the Library Explorer, and let's find math operations, and let's choose sum. Now let's drag and drop the sum component into the schematic. Now you can connect them. Double-click the sum component and change signs. Instead of to, type minus plus. Now you can also add a gain. Again, drag and drop it into the schematic and connect it. Another set of features worth mentioning are features that are jointly called SCADA inputs. Let's find them in the Library Explorer. SCADA inputs allow you to set values in real time when you are interacting with the simulation in HIL SCADA. For example, let's change the name of this SCADA input component to reference. Double-click the component name and change it. Also, let's change the voltage source with signal control voltage source. So you can delete it by selecting it and pressing the delete key. Now use the Library Explorer to find the signal control voltage source. Let's drag and drop it like so. Now we can close the loop here. One other thing that you should be aware is that you can set initial values for each component for which that is relevant, such as the voltage source that you've just deleted. So again, let's practice dragging and dropping. Let's find that component and place it into the schematic, like so. So if you double click it, you can see that you can set the initial value for the voltage source. It is possible to initialize the voltage source by typing in the corresponding voltage and choosing the source nature. These values can be set before and during the simulation in HIL SCADA. Of course, you can also use the model initialization scripts for this purpose. This capability for this component was introduced in Typhoon HIL Control Center version 2019.4. If you're using an earlier version, it may not be available. Okay, you can again delete this component. Good. So let's take a look at the model that we've just built now. You can see that here you have some blocks that are colored in black and some that are colored in blue. These colors indicate two different parts of the schematic. The part colored in black indicates the electrical part of the system. That is the part that runs in real time with up to 200 nanoseconds high fidelity simulation in Typhoon HIL FPGAs. The time step depends on the HIL emulator which you are using. The part colored in blue indicates the signal processing part that runs on the general purpose CPU and typically runs at different execution rates, as you can see from here. Where? Just double click the voltage measurement. As you can see, right now it is set to 100E-6. The signal processing part is generally used for controlled loops that are implemented here in the model. With this, you have gained the basic skill set necessary to use the Typhoon HIL Schematic Editor. Now, feel free to play around and explore all the components and blocks that you have here at your disposal in Library Explorer.